A long rope is lying on a smooth horizontal surface. A force F is applied at the front end of the rope and it accelerates. You would like to find the tension at a distance x from the rear end. Now, we are not given the mass of the rope and we cannot idealize the mass as 0. We cannot consider this as a massless rope. That give an infinite acceleration for this. F is some finite value. If mass is 0, mass will never be 0. We idealize the mass as 0. Or better still, we should say we can ignore the mass of the ropes if there's some of the bigger masses attached to it or something. Not in this case when there's nothing else attached to the rope. So if you're interested in tension in the rope at a distance x from the rear end, well, the force on the rear end is due to the pull by the front end, the portion to this side. Now this, if you call it T is causing acceleration of the portion of length x. So you could write T is equal to m, mass of this is say mu times x into acceleration. To find the acceleration, we can consider the entire length of the rope, which is say L, and the acceleration A would be then F by mu L, right? The acceleration of the rope. Well, all parts of the rope have same acceleration, and so you could eliminate that A here, then mu goes away, so T equals mu into x by L. This you substitute for A as F by mu L. This will give us mu goes away, x by L into F. So tension varies linearly as x changes from 0 to L. It's F at the front end and 0 at the rear end. Tension is varying here. We generally ignore the mass of the rope and then say tension is same throughout. Not in this case. You cannot ignore the mass. That will give an absurd result. And also, well, tension is varying along the length. Supposing we had a large mass attached to the rope, a large mass on a horizontal surface. In this case, if we ignore the mass of the rope, nothing absurd happens. If you ignore the mass of the rope, you don't say it's negligible mass. You don't say massless. You should say negligible mass. And if this mass can be ignored, then you can see the rope as straight, no sag. So then F by m would be the acceleration of this block. So the force F applied to the front end of the rope is exerted by the rope on the block of mass m. So acceleration is F by m. A rope allows you to conveniently apply a force on an object which is some distance away from you. Mind you, you can only pull an object using a rope. You cannot push. So you can have only tension but not compression. Rope does not withstand compression. If you imagine holding a rope between your fingers, well, if you try to bring them closer, the rope will sag. So if you try to stretch them, we idealize the ropes as inextensible and they won't stretch. So ropes resist tension but not compression. So when you apply a force at one end of the rope, well, the force applied by the rope on the object at the other end. So that's what we use the ropes for. Suppose we have a rope hanging from a ceiling. The rope is of length L. There's nothing attached at the lower end of the rope. Suppose you want to find the tension at distance y from the lower end. This is y. Well, again, tension varies here. There's nothing pulling at the lower end of the rope here. There is no tension there. Tension is 0 here. The entire weight of the rope pulls on the ceiling and the ceiling exerts an upward force on the rope here. So we have, well, due to gravity of course, you can write a simple equation here. If the tension is T here, well, This tension is supporting the weight of this section of length y. So T is mu yg. And if the length of the rope is L and mass is m, this mu would be m by L into g into y. That's the tension. Again, the point we are trying to make is tension varies along the length of the rope. Right? Tension is 0 here, and at distance y from the lower end, it's mgy by L. At midway point, it will be half the weight, because half the weight of the rope, half of the rope is below that point. So the upper segment of the rope would be exerting a force of, supporting the weight of the lower portion, which is mg by 2. And that's what we have here. Now suppose we hang a large weight at the lower end here. Suppose we hang a large weight here, and this m is very large compared to the mass of the rope. The tension at the lower end would be mg, because that will be supporting the weight of the block here, and the tension here, at the upper end, will be the entire weight of the rope plus the block must be supported here. So that will be m plus small m here. T is m plus T equals m plus m into small g, and here it is T at the lower end, let's say T dash, let's say is mg. If m is very, very small compared to mg, you can ignore the difference between T and T dash. That's what we normally do. Same tension throughout, we say. That's because if a large mass is hung from the end of the rope, we can ignore the change in tension. So the same tension throughout. Also, if it's a single rope, you can ignore the mass of the rope. But imagine holding it with your fingers and then sliding your fingers, or just holding it and then pulling it down a bit. So on the surface of the rope, you're exerting a force. So tension in the segments on either side will be different. Single rope must have same tension throughout. No tangential forces on the surface. That's what we want. If there are tangential forces on the surface, you can just hold it, pinch it a bit, and then pull it down a bit. Tension in the segment above will be greater than tension in the segment below. Suppose we have a situation like this. We have a large weight hanging from two supports, say at the same horizontal level. Strings are of equal length. There's a block of mass m. Now if T is the tension here, this tension in the lower segment here will be equal to weight of the block, right? The block pulls on the lower end of the rope with the force mg downward. The rope exerts that force, so there's a tension of capital mg in this. We can ignore the mass of the rope here if this very, very large weight we are hanging compared to the mass of the rope. Then 2t cos theta equals this tension, which is equal to mg. Simple enough. We can ignore the mass of the rope in case there is a large mass hanging there. But suppose we have a situation like this. We have a rope hanging between two supports. There is no mass hanging from below. This would sag. It will not be straight segments anymore. It will sag. The shape has a name. It's called catenary. And if you hold a rope and then don't have any tension there, you can see that curve. That's called a catenary. Well, supposing this is a tension F here, and this angle is theta, we can consider 1/2 of this here, and for this 1/2, it's tangent to this is horizontal here. So if tension here is T, and tension here is of course F at an angle theta here, so F cos theta is going to balance the weight mg by 2 of this portion. So F cos theta equals mg by 2, and T is F sin theta. F sin theta is equal to T. So what is the tension at the bottom? We can find that. Divide this and you'll get F theta, tan theta equals G by mg by 2. So if you know that angle, you can find the tension at the bottommost point. Tension at the bottommost point is 0. This segment is held by a force exerted to this side, right? This segment. If you cut the rope here, this would fall this way and this would fall this way. This portion is held by the force acting this side. So tension is varying along the length here because we are saying there is nothing hung from the rope. If there is something hanging from the rope, which is large in weight, you can ignore the mass of the rope, and that gives us a nice situation. Ropes will be straight, no sag. There is a sag here. If you observe the electrical wires between two towers, you can see there is a sag there. That's a catenary. So in other words, tension in a rope can vary. Ropes are not massless. We can ignore the mass of the rope in comparison with something. In some situations, ignoring the mass of the rope will give you very bad results.